Welcome to this class. So we continue looking at atomic structure. So last time we looked at formulas, okay, the familiar formulas that we're going to be using under atomic structure. Okay, we had a formula that related the speed of light, okay, to the frequency and the wavelength. Okay, so we can write this equation in general, not just specifying it to the speed of light. We can just say any speed, let's say v, is equals to the frequency multiplied by the wavelength. Okay, and then we also had the formula for calculating the energy. So we said energy was equals to the Planck's constant, okay, multiplied by the what? By the frequency. Okay, so if we make the frequency the subject of a formula from this equation here, what we are going to have is the frequency will be equals to the speed divided by the what? The wavelength. So from this formula here, we can say energy is equals to the Planck's constant, and then where there's F here, we put the speed over the what? The wavelength. So we end up with Planck's constant multiplied by the speed divided by the what? By the wavelength. So this was one of the equations that we said we are going to be using when we are calculating energy. And then the other one is the Einstein's formula that just states that m and then c squared. So this is when you are specifically looking at the speed of light. C represents the speed of light. But what if you are just looking at any other speed which is not of light? Then we are going to write mv squared. Okay, so if energy is equal to mv squared, and again here energy is equals to this, it means we can equate this part to this in order to obtain an equation, okay, that can help us find the mass of a particle. So we said mv squared is equals to hv and then divided by the wavelength. Okay, so from there we can get an equation, okay, entirely an equation that can help us find this mass. So we can say mass is equals to, and then both sides we divide by this v squared here. So we are going to have hv divided by lambda, then divided by v squared. So dividing by v squared is the same as multiplying by 1 over what? V squared. So the hv is still here over lambda and then multiplied by 1 over v squared. So from this we can see that this v will cancel and one of the v's here will cancel. So meaning our mass will just be equals to h multiplied by 1, I remain with h, divided by lambda multiplied by the v. So this is lambda multiplied by the what? The velocity or the speed. Okay, so that equation there is very important in answering this question 1 that you can see here. So let's go over question 1. So in question 1 they're saying an atom of a particular element is traveling at 3 times 10 to the power 6 meters per second. So that would be our velocity, or our what? Our speed. Okay, and then they are saying the de Broglie's wavelength is found to be this one here. Okay, so it means our wavelength is just 3.3185 times 10 to the power minus 15 meters. Alright, so now the question comes, which element is this? Okay, so how can we find out what element is this? So the trick here is first of all to calculate the what? The mass. And then after we calculate the mass, we can convert that mass into the atomic mass units, or what we call as the molar mass. Okay, and then once we have the molar mass, we can just compare it with the elements on the periodic table to know what element it is. So let's calculate the mass. Okay, so the mass here will just be equals to, this h is a constant we call the Planck's constant, and it has a value of 6.626 multiplied by 10 to the power minus 34. And then here we divide by, okay, the wavelength, which is 3.3185 times 10 to the power minus 15. So this is what we have, okay, and then multiplied by the speed. So the speed is this guy. So 3 times 10 to the power 6. This is our speed. Okay, so this shows that our mass is equals to, so the best way that I told you from the previous class, I said you separate whatever has 10 to the power something, you put them together, and then whatever does not have any 10 to the power something, you also put them together. So I'm going to say this is the same as 6.626, okay, divided by, here I have this number, I'll write it here, 3.3185 multiplied by the 3, okay, and then I'll say times, and then I now put these numbers that have 10 to the power something. So I have 10 to the power minus 34 divided by, here I have 10 to the power minus 15 multiplied by, here I have 10 to the power what? 6. And then you can easily evaluate this by just using the exponentials. We know that if the powers, if the bases are the same and these things are multiplying, we just add the powers. So it means here below there we're going to have what? Here on top we have 10 to the power minus 54 divided by, here we just add the powers. So minus 15 plus 6, we're going to get 10 to the power minus 9. And then there it will just be 10 minus 34 minus 9. Because here we are subtracting because we are dividing these two. Okay, so what is 34 minus 34 plus 9? Because here it will be minus multiplied by minus, so this will be a positive. So that just gives me 10 to the power minus 25. So this part is just 10 to the power minus 25, and then now you can punch this part onto your calculator. Okay, so whatever you're going to get here, you just say times 10 to the power minus 25, and that will be your what? Your mass. Okay, that will be your what? Your mass. So from there now, let's punch in this guy here. We see what we are going to get, and then we combine it with 10 to the power minus 25. Okay, so if I punch this onto my calculator, I'm getting my mass is equals to, so if I punch this and then I combine it with, here we found it was 10 to the power minus 25, right? So if I combine it with this, I'm simply getting 1.66 times 10 to the power minus 27. Okay, and the mass that comes out from this formula is always in kgs, so this is kg. Okay, so it means the mass is kg here. Okay, and then now we can convert this mass into the molar mass, okay, or what we call as the atomic mass what? Units. Okay, so there we need a ratio that we need to use on converting the atomic mass units to mass, or mass to the atomic mass units. Okay, so that equation, okay, that equation is given by 1 atomic mass unit, okay, or 1 molar mass, which is moles per gram per mole, okay, not moles per gram, but gram per mole. Okay, so one of these is equal to the mass of 1.667 times 10 to the power minus 27 kgs, like this. Okay, so here we found our mass is this, which is almost similar to this. So if we put this mass there times 10 to the power minus 27, okay, we found it was kg, and then we say this is x, so we can cross multiply here. So if we cross multiply, definitely we are going to get our x. It's just, since this number here is almost the same as this, so our x will just be 1 atomic mass unit, or it will be like 0.999, something like that. Okay, and then now you go on your periodic table, you look for an element that has the atomic mass unit of 1, or the molar mass of 1. So when you go on that periodic table, that element will just be what? Hydrogen. So that's how we are going to identify that element. So we're going to say that element is hydrogen, and then the last question here, they are saying write the electronic configuration for the element you found. So the electronic configuration, okay, so the hydrogen atom only has 1 orbital, which is the s orbital, and it also has 1 shell. So the electronic configuration of hydrogen is just 1s, and then we put the 1 electron that is present in the what? The hydrogen atom. Okay, so this will be the answer for part B, and then the answer for part A was this one, the hydrogen. Alright, so we are done with question 1. Let's look at question 2. Okay, so question 2, they're saying the Heisenberg uncertainty principle can also be expressed in the form of change of energy multiplied by the change of time is greater than or equal to h over 4 pi, okay, where E represents the energy, T represents the time. Show that the units for the form above are the same as the units for the form below. So we have two formulas, and then they're just simply asking us to show that the units of this guy will be the same as the units of this guy. Okay, so you have to remember your base units. Okay, those 7 base units, the meter, the length, they're the one that are going to help you here. So in the first formula, we have the change of energy multiplied by the change of time is greater than or equal to h over 4 pi. So this is what we have. Okay, so what are the units for time? So the SI units for time are just the what? The second. So I'm going to write S there. And then this one is energy. What are the what are the units for energy? Okay, so we know that energy, its units are just joules. Okay, but how does this joule come about? Okay, so this joule is a combination of it's a combination of 3 base units. That's the mass, the length or the distance, and the what? The time. So if you get any formula for energy, okay, that you can use to calculate energy. Let's say I get the formula for calculating kinetic energy, which is just half mv squared. Okay, so we know that from this I can come up with the units for this kinetic energy. So this mass here, we know it's measured in kgs. Okay, and then this v is the velocity. So velocity is measured in meters per second, right? So where there's v, I'm going to put meters per second, but since this v is squared, I also square this one like this. Okay, so the units for kinetic energy is just kg multiplied by this 2 goes to the m, makes m squared, divided by, goes to the s, it makes s squared. So these units here, okay, kg multiplied by the meter squared and then divided by second squared are what we call as the joule. Okay, so you can pick any formula for finding energy, you're still going to find the same thing. So if I pick the formula for potential energy, maybe potential energy is equals to mgh. Okay, m is the mass, so that's the kg multiplied by the g is the gravitational acceleration, right, which is measured in m per squared, like that. Okay, like this, and then the h is the height. So the height is the same as the distance or the length. It is measured in what? Meters. Okay, so if I multiply this, what I'm going to have is kg. This m will multiply with this m, so it will be m squared, and then I still have the s squared down there. Okay, so you can see these units and these units are the same. So these units here are what we call as the joule. Okay, these are the units for the joule. So energy is measured in joules, which is the same as this. So I'm going to put here kg m squared and then divided by s squared. Okay, so what will be the units now for that first formula if we combine whatever we have here? Okay, so if we combine whatever we have here, we see that this s is going to cancel with this one of these s. So we have kg m squared and then divided by s. So these are the units that come out from the first formula, this one here. So we can write them here. So you say from this formula we are ending up with kg meter squared per second. Okay, so are we going to end up with the same units if we use this formula here? Okay, are we going to end up with the same units? So let's try. So in the second formula we have the change of x and then dot m and then change of v. Okay, and then greater than h and then 4 pi. Okay, so from there let's get the units that we can see. Okay, so this is the change of x. X is the displacement. So this x here is measured in meters multiplied by this m here is mass, so I'll put kg, and then this is the change in velocity. Okay, so the velocity, we said it's measured in meters per second. Okay, you can write it as meters per second like this, and then whatever we have here. So we see that on the left hand side here we're just going to have m multiplied by kg multiplied by m, which will give me kg m squared and then divided by s. Okay, so we see that from the second equation as well we are going to end up with kg m squared and then divided by what? By s. Okay, so we've shown that this first equation and the second equation there, they have basically the same what? Units. Okay, so that's how you show that one. Okay, question 3, they say use the periodic table to identify the element with the electron configuration 1s2, 2s2, 2p5. Okay, so how can we identify this element? First of all, we just have to count the total number of electrons. So we have 2 electrons here, 2 electrons there, and then 5 electrons there. So the total electrons will just be 2 plus 2 plus 5. So this will give you what? 9 electrons. Okay, so what do you do with your 9 electrons? Okay, so if this element has 9 electrons, it means it has what? 9 protons. Okay, because they said we have to use the periodic table, so I'm assuming that these are not ions, so no electrons lost or no electrons gained. So if we have 9 electrons here, it means we have 9 what? Protons. So this 9 protons here indicates the proton what? Number. Okay, so the proton number is also the atomic number. So you just go on your periodic table and then you search for an element that has the atomic number of what? 9. So when you search on your periodic table, the element that has the atomic number of 9 is simply what? Fluorine. Okay, so you're going to pick fluorine there. So you have used the periodic table to identify that element with the given what? Electron configuration there. So that's how you do question 3. And then let's look at question 4. Okay, so question 4, they're saying how many electrons are permitted in the subshell. A, we have L is equals to 0, and then here on B we have L is equals to 3. So what does L, okay, what does L represent? Okay, so there are 4 quantum numbers. Okay, so the first one is the principal quantum number. So the principal quantum number, I'll just write them here. So principal quantum number is represented by the n. Okay, and the principal quantum number tells you the energy level where you are, or the energy of the orbitals. Okay, and then from there we have the angular quantum number. Okay, so the angular quantum number is represented by L. Okay, let me say angular quantum number here, and then this angular quantum number is represented by L like that. Okay, and the angular quantum number tells you the shape of your orbital. Okay, and then from there we have the magnetic quantum number. So this magnetic quantum number, it's represented by ML like that. Okay, so the magnetic quantum number tells you the orientation of the orbital in space. Okay, and then the last one is the spin quantum number. So what does the spin quantum number tell you? It tells you the direction of the electron. Okay, so if the electron is facing upwards like this, then the spin quantum number will just be plus 1 over 2. And then if your electron is facing down like this, then your spin will just be minus 1 over 2. So these are the 4 quantum numbers that you're going to come across. Okay, so now depending on the quantum number that you've been given, okay, you can find the rest of the other quantum numbers. So if I have L, okay, so from this if I have n, I mean from this n, which is the principal quantum number, I can get my angular quantum number, angular momentum quantum numbers. So from this L, or from this n, if I have n, okay, then it means my angular momentum quantum number will just be 0 to n minus L, n minus 1, I mean. Okay, just be 0 to n minus 1, and then the magnetic quantum number is from negative L all the way up to positive L, but including 0 somewhere in between there. Okay, and then the spin quantum number is just depends on the direction of the electron. Okay, so it can be plus half or minus half. So for example, if my principal quantum number here is 1, okay, then it means my angular momentum quantum number will just be 0 or what? 1, because we say this angular quantum number takes the values from 0 all the way to n minus 1. Okay, so in short, here in fact this one won't be there, but we just have the 0 there because it takes numbers from 0 up to n minus 1. So if I write my first if I write my first quantum number under this column as 0, and then the next one should be n minus 0, but the n is 1, so this is n 1 minus 1, so it still gives me 0. Okay, and then here it means I'll just have 0 as my magnetic quantum numbers. So if my n is 2, okay, then my angular momentum quantum numbers will run from 0 all the way to n minus 1. So the first one will be 0, okay, and then the next one will be 1. So how do I get this one? Is when I've subtracted the n, which is 2, minus what? 1. Okay, so for this one here, I'll have 0 as the magnetic quantum number, and then for this one, remember we said from minus L all the way up to L, okay, but including 0. So minus L, so this is the L, it's 1, so I'll write minus 1, 0, and then what? Positive L. So this is what I'm going to have here. So this knowledge here is what we are going to be using in order to find the answer here. Okay, so now there we have L is equals to 0. Okay, so L is equals to 0. It means what was our principal quantum number? Okay, it means here the principal quantum number was just 1. Okay, so N, I'll write like a box here, and then L, and then ML. Okay, here we can even put the spin. Okay, so we can say if my L is 0, then it means my principal quantum number was just 1. Okay, and then what will happen to the magnetic quantum numbers? To just be what? 0. Okay, and then if I go on B, if my angular momentum quantum number is 3, okay, what does it mean for the principal quantum number? Okay, so the principal quantum number, it means it is 4. Okay, it means the principal quantum number is 4, because from this one we can get 0, 1, 2, and 3, which is this 3 here. Okay, so if L is 3, then here I'm going to have minus 3, minus 2, minus 1, 0, 1, 2, and then what? 3. Okay, so the question here was how many electrons are permitted in this subshell. Okay, so this magnetic quantum number here indicates the number of orbitals. Okay, indicates the number of orbitals. So there where we have 0 here, okay, it means we are only permitting 2 electrons, because this 0 here does not indicate that you have 0 orbitals. No. So if you have 0 there, it means the orbital that you have is just the s orbital. If you have 1, the orbital that you have will just be the p orbital. If you have 2, it will be the d. If you have 3, it will be the f. Okay, so if you have 0 angular momentum quantum number there, it means you are looking at this orbital here, which is the s. So what is the maximum number of electrons that the s orbital can hold? It's just 2. Okay, and then this one is 3. So if this one is 3 here, it means the orbital is f. So what is the maximum number of electrons that the f orbital can hold? It will just be 14. Right, so that's the explanation behind that. Okay, but if you want, you can just use this simple formula. I was just explaining that so that you know where it's coming from. Okay, you're going to say the number of electrons that are permitted in a certain subshell is given by the formula 2L plus 1. Okay, this will give you the number of electrons that are permitted. So here our L is 0, so it will be 2, 0 plus 1. So this will be just be 2, and then I have 1, so it will mean 2. So it means the number of electrons that are permitted in L0 will just be what? 2. Okay, so you can also use this simple formula here. Okay, what about if my L is 3? Then it means I'll have 2 multiplied by 3 and then plus 1. So this will give me 2, and then inside the brackets I have 6 plus 1, okay, which is just 7. So it means the number of electrons permitted here will just be what? 14 electrons. So you can use this short version, okay, or you can use the other one where I was explaining in everything. So it's up to you. Okay, so let's look at question 5 now. So question 5, that's where you really need to use the approach that I gave on the other question that we are from solving. So here they are saying using the angular momentum quantum numbers, magnetic quantum numbers, and orbitals, show that the total number of electrons that can be presented in the principal quantum number 4 is actually what? 32. Okay, so what we are going to do here, is this. We are going to draw up a box like so. This will be the box that we are going to draw. Okay, maybe I add another one before this one. So I add another one here, and then okay, so 1 2 3 4, okay, and then 5, and then 6. Okay, so this is the table that I'm going to draw up. So in this first column here, I'm going to put the principal quantum number, okay, and then here I'm going to put the angular momentum quantum number. Then here I'm going to put the subshell or the sub level, okay, and then here I'm going to put the magnetic quantum number, okay, and then from the magnetic quantum number I'm going to put the number of orbitals here, number of orbitals, okay, and then the last one here will just be the number of what? Electrons. Okay, so here we are dealing with N4, so I'll write 4 here. So remember the L, it is all the numbers from 0 all the way to what? N minus 1. So I'll start 0, 1, 2, okay, and then N minus 1 is just what? 3. So those are the angular momentum quantum numbers that I'm going to get from this N here. Okay, and then based on the number that is here, I can give a name to this sub level. So if you have 0 here, it means the sub level will just be S. Okay, the orbital will just be S. But that S is occurring under what? The N4. So it will be 4S. And then this one, if it's N, is the P. Okay, but it's occurring under the 4. So it will be 4P. And then this one is 2. So it will be 4D. Okay, and then this one here, it will be 4F like that. Okay, and then now we can get the magnetic quantum numbers. So we said the magnetic quantum numbers start from minus L to 0 to positive L. Okay, so here we just have 0 as our L, so it means the magnetic here will just be 0 as well. And then here we have 1, so we have minus 1, 0, and then 1. Here we have 2, so it will be minus 2, minus 1, 0, 1, and then 2. Here we have 3, so we start from minus 3, minus 2, minus 1, 0, 1, 2, and then 3. Okay, so depending on what you have here, those will be the number of orbitals. So here I can only see 0, so that will mean I have 1 orbital. Here I have 1, 2, 3, so I have 3 orbitals. Here I have 1, 2, 3, 4, 5. I have 5. Here I have 1, 2, 3, 4, 5, 6, 7. Okay, so each orbital can contain a maximum of 2 electrons. So if I have 1, it means the number of electrons here will be 2. If I have 3, the number of electrons will be 2 multiplied by this 3, which will be 6. If I have 5, it will be 10. If I have 7, it will be what? 14. So it means the total electrons that can come out from the quantum number 4 here, the principal quantum number 4, will just be the addition of all these. So 2 plus 6 plus 10 plus 14, okay, it will actually give you what? The 32, which is the required one, as we are told here. Okay, so we have shown that here. So okay, so let's look at question 6 now. So question 6, they're saying calculate the product of uncertainty of displacement and velocity of a moving electron. Okay, so according to the principle, we said the change in displacement multiplied by mass multiplied by the change in velocity is greater than or equal to the Planck's constant divided by what? 4 pi. Okay, so here they have said we calculate the product of the uncertainty of the displacement and velocity. So what we are calculating here is the change in x multiplied by the change in v, because this is the displacement, this is the velocity. Okay, so we can see them in the formula there. So it means we have to know this mass here. So the mass here, they're saying the velocity of a moving electron. Okay, so the electron has a fixed mass. Okay, so the mass of an electron is just 9.11 times 10 to the power minus 31 kgs. So this will be the mass. Okay, so here I'll write it in this form. I'll say the change in x multiplied by the change in v, and then multiplied by this m here, which is the mass of the electron. So it will be 9.11 times 10 to the power minus 31 is greater than or equal to h is the Planck's constant, which is just 6.626 times 10 to the power minus 34. And then we are dividing this by what? 4 pi. Okay, so we want to make the product of the displacement and the velocity as our subject of the formula. So what we have there will be, okay, change in x multiplied by the change in v will just be equals to greater than or equals to this guy here, and then divided by this. So what we are going to have there is this. Okay, we are going to 6.626 multiplied by 10 to the power minus 34 divided by 4 pi. Okay, but remember this one here has also gone the other side by dividing here. So we are dividing by 9.911 times 10 to the power minus 31. So this is what we are doing here. Okay, so here it means we just have to punch this onto our calculators. But before you do that, maybe you would want to simplify things there. Okay, so you can say this here is the same as this. Okay, so I have 6.626 times 10 to the power minus 34 divided by 4 pi, and then this one is division, so we can write it as multiplied by 1 over 9.11 times 10 to the power minus 31. Okay, so this one now is looking nice. And then from here we're going to say greater than or equal to to be 6.626 divided by 4 pi multiplied by 9.11, and then these with powers we take them to be alone, so it will be 10 to the power minus 34 and then divided by 10 to the power minus 31. Okay, and then now we can punch this into the calculator and combine them with this. So once we do that, we are going to end up with 5.79 multiplied by 10 to the power minus 5, and this will be m squared per second. Okay, so those are the units that we're going to use there. So this will be the product, okay, of uncertainty of the displacement and the velocity. Okay, so now let's look at question 7. So question 7, they're saying which of the following orbital designations are incorrect. So we have 1s, 1p, 7d, 9s, 3f, 4f, and then 2d. Okay, so this table that I've put here, okay, is going to help us determine if it's correct or not. Okay, so this 1s here, you can see it's there. Okay, if our n is 1, and then we are going to have 1s there. So this one here, the first one, okay, is correct. What about 1p? Okay, so can we see 1p anywhere here? We can't see 1p. Okay, why can't we see 1p? It's because the p orbitals start when the n is 2. Okay, so this 1p here, it means that my n is 1 here. Okay, but the p orbital here, you can never find it in the first energy level. Okay, the p orbitals start at n2, so you can see that n2 here, and then if I come to my orbitals here, okay, you can see a p somewhere. Okay, so we are going to say that one there is what? Incorrect. Okay, so this one is incorrect. And then 7d. Okay, can 7D be valid? Yes. Okay, 7D is valid. Why is it valid? When n is equals to 7, okay, from this n is equals to 7, we can get a lot of orbitals. Okay, remember we said L starts from 0 all the way to n minus 1. So from this we can get 0, 1, 2, 3, 4, 5, 6. It will end at 6 here, because this 6 here is the n minus 1. So 7 minus 1, it ends at 6. So the 0 is the S, the 1 is the P, okay, the 2 is the D. So if I have 7D, so this one is 7, and then here I have D there. So it means 7D here is correct. It exists. So we're going to mark this one. And then the 9S also exists when our n is what? 9. So our n is 9. I'm going to have 0, 1, 2, all the way up to 8. So this 0 here will correspond to 9S. Okay, and this is what I'm seeing there. So this one is correct. What about the 3F? Okay, so 3F is not going to be correct because the F orbitals start at 4. So we can look at this table here. So if my n is 3, can we see any F here? No. Okay, but if my n is 4, we can see an F there. Okay, so the F orbital starts when n is equals to 4. But here we have 3F, meaning our n here is what? 3. So this one here is incorrect. So we're going to cancel this one. And then N4, definitely it exists. You can see it there. Okay, and then 2D. Okay, 2D does not exist. Okay, because if our n is D, our n is 2, I mean, okay, the angular momentum quantum number that we can have from n is equals to 2 is just 0 and 1. Okay, and 1 is P, 0 is S. So we don't see any D here. So it means even this 2D here is wrong. Okay, so we have determined which ones are wrong and which ones are what? Are correct. So the ones that were wrong are the 7D, okay, the 1P, and the 2D. So these ones here are not correct. Right, now let's look at the last question for this video. So the last question here, they're saying a boron atom has 5 electrons. Write the 4 quantum numbers. Okay, write the 4 quantum numbers for the for each of the 5 electrons in the ground state. Okay, so here first of all we have to write the electron configuration. So the electron configuration here is 1s, 2s, and then 2p. So in the 1s we have 2 electrons, in the 2s we have 2. Okay, so this is 4. So remember we had 5 here, so we are remaining with 1. Okay, so that will be the arrangement there. So if they want us to calculate, okay, or to find the 4 quantum numbers of each electrons that are here. Okay, so here we have 2 electrons. We have to find their 4 quantum numbers. Okay, even here, even there. So remember we said the 4 quantum numbers are the principal, okay, the angular momentum, and then we have the magnetic. Okay, the magnetic is ml, and then we have the ms, which is the spin quantum number, right? Okay, so what I'm going to do here, I'm going to write a table. So I'm going to write electron here, and then from electron I'll write n, and then l, and then ml, and then ms. Okay, so the first one here, okay, if I get an electron from here, because in this first orbital here there are 2 electrons. Okay, so if I get the first electron, okay, from the 1s, what will be the 4 quantum numbers that it will have? Okay, so we see that the n there is just 1. So the number that is in front of the orbital there, that is always our n. So our n is 1. So it means this one here will just be 0. Okay, because we said this one takes 0 all the way to n minus 1. Okay, so I get 0, and then n minus 1, our n is 1. So our 1 minus 1 still gives me 0. And then this one here, okay, takes the values from minus L, including 0 all the way up to positive L. But here we just have 0, so it will take 0. Okay, and then the direction here, which is the spin, we can choose. So let's say the first one is looking up like this. so it means it will be plus half. If it's looking down, to be minus half, so it means this one will just be 1 over 2. Okay, plus 1 over 2. And then if I get the second electron, okay, from the 1s, it means I'm going to have 1 0 0. But here now on the spin, because the first one was looking up, it means the second one should look down, so I have minus 1 over half. Okay, so I'm done with the ones from the 1s. I go to the 2s. Okay, so I'm going to say the first 2s electron. Okay, so the n is 2 because the 2 is the number that is in front of this orbital. So we have 2, and then this one here will take the values 0 all the way to n minus 1. So n minus 1 is just 1. Okay, so those will be the quantum, those will be the numbers there for the angular momentum quantum. Okay, yeah, and then what else there? Okay, we can find the magnetic. Okay, so the magnetic, we said it is which one? Okay, so the magnetic, okay, depending on which one you are getting here. Okay, so if you find two values for a certain quantum number, you always pick the lowest. So this one here I found 0 and 1, right? So I'm going to pick the lowest from this one. Okay, so from there, here I'm just going to write the 0. So I'm just going to write the 0. But remember, we have two values of this L. We have 0 and 1. So if you have more than one quantum number, you pick the what? The lowest. So no wonder I've written 0 here. And then the one that will correspond to this will just be 0 here. Okay, and then the charge here will just say plus 1 over 2. Okay, and then the second 2s electron, okay, will take up the same things here. So it will just be 2. Here there will be 0 and 1, but you pick the smallest, so it will be 0. And then here it will just be 0. And then here now, since the first one was looking up, no wonder we have a positive, the other one should look down. So we have minus half. Okay, so we are only remaining with this guy here, which is the 2p electron. Okay, so the 2p electron, we only have one of it. So I'm going to write it on top here. Okay, so I'm going to say the 2p electron. Okay, so the 2p electron. Okay, so we have one electron here. So what will be the n value for this one here? So the n value here, I'll write them on top here to just be 2. Okay, and then the L there will just be what? Okay, the L there we are going to put 1. So why are we putting 1 here and there we put 0? Because this one was in the 2s. No wonder we're putting my zeros here. But this one here, okay, is in the 2p. So we have to put 1 there. Remember, this L here represents the orbital. Okay, so that's the other way you can look at it. So here we're going to put 1 because it's the p there. Okay, and then from there we can get the ml. Okay, so the ml, since this is 1, we're going to have minus 1, 0 and 1. So we said if we have more than 1, we pick the lowest, so we're going to pick minus 1. Okay, and then this one, the spin, we're going to pick the positive one like this. Okay, but some other guy can pick the negative one, it is still correct. Okay, so these here are the set of all the four quantum numbers, okay, of all the 5 electrons that are present in the what? The boron atom. So the first one here, the first electron has these quantum numbers, the second one has these ones, okay, the third one these, the fourth one these, then the last one, which is the fifth one, it has those. Right, so that's all for this video. We've looked at about 8 questions. Okay, so we are going to continue looking at atomic structure in the next video. Okay, so those who would like to access the full videos, okay, for other topics, okay, we have videos on all the other topics. Okay, you can check the link in the description below. Okay, it's going to give you a video guide, so you watch that video on how you can register, and then afterwards you go to the website. That's when you're going to register. Right, so we also offer tuitions for math, physics, biology, and some second year courses, okay, such as linear algebra, calculus, probability, and also statistics. So if you are interested in all that, find them in the link below here. So thank you so much.